Now, why is it that deep learning, after all of these years in AI, that deep learning is becoming such a large hammer? It's like Thor's hammer. It fell from the sky. It was like that big of a deal. Well, the reason for that is because deep learning, as wonderful and as beautiful as a concept as it is, and as much innovation that's still happening, it's a concept that's relatively easy to apply. You can actually use some of these frameworks that are being developed. TensorFlow, for example. You could use some of these frameworks that are being developed and develop your own, train your own network with the data that you have. Every organization in every single company should have the ability to use these frameworks to train their networks. The beauty of deep learning is that it's approachable, it's powerful enough, as you see, it's powerful enough to actually achieve superhuman results without superhumans to train them. Achieving superhuman results without superhumans to train them, without superhumans to code programs into them, is a big deal. It's one of the reasons why industry after industry analyst is now predicting that deep learning is going to be a very, very big industry. Now, I think that deep learning is not going to be an industry. Deep learning is going to be every industry. Deep learning is not going to be an application. Deep learning is going to be in every application. Deep learning is a brand new computing model. Analyst after analyst, however you think about it, they're big numbers. $40 billion by 2020 is one estimate. Over the next 10 years, $500 billion. John Kelly, my friend at IBM, head of Watson, they believe that cognitive computing, or discovering insight from IT, instead of just IT, discovering insight from IT, cognitive computing, will be a $2 trillion industry. It makes so much sense. Our goal is not to have computers. Our goal is not to be productive. Our goal is to have insight. Insight in business is more powerful than anything. We think this is going to be a big industry as well. And in fact, it's already our fastest growing business. It is starting to show up. After working on this for about 5 years, we've created 2 products that hyperscale companies can adopt and use in production. We call it Tesla M40 and Tesla M4. The Tesla M40 is intended for training. The Tesla M4 is intended for inferencing or production of that network. Now, Tesla M40, you could imagine, is quite a beast. Tesla M40 is a beast of a GPU accelerator for deep learning neural net training. And then we have this little cute thing here. This is the M4. And you put these in 1U machines. Every single rack of hyperscale computing can adopt this. Less than 50 watts. And as you heard earlier, because of GIE, our GPU inference engine, the GPU inferencing energy efficiency is off the charts. 20 images per second per watt. And so as a result, there's just no reason to use FPGAs. There's no reason to design dedicated chips. This GPU is not only energy efficient from a perspective of classification and inferencing, it's also universal. If you wanted to do video transcoding, not a problem. If you want to do image processing, not a problem. All of those capabilities of these 2 GPUs, exactly the same. This one is designed to be as fast as possible, and this one is designed to be as energy efficient as possible. Tesla M40 and Tesla M4. These 2 products, since announcement, just earlier this year, has become our fastest growing businesses, and it's been adopted by internet service providers all over the world. Any company that has a large number of customers, large amount of data, large amount of content that they want to sort through and recommend, which is just about every internet company in the world, every internet service provider in the world, could really benefit from Tesla M4 and Tesla M40. We're super delighted with its progress, and there's now every evidence that deep learning is going to be a very large industry. It's not just research anymore. I think it's absolutely industrial, and it's going to be every industrial. Well, the thing that's really amazing is this. Deep learning so far has been using one basic approach. Largely, what is going into production is supervised learning, meaning you tell the computer what this thing is, and you train it to repeat it, to recognize it, to predict it in the future. And you keep telling it, you're wrong, and until one of these days it figures out what the right prediction is. This is an apple, this is a dog, this is a car. That approach of training is arguably quite laborious. And the reason for that is the vast majority of the world is not labeled. The vast majority of the world is not labeled. There are so many other things we like to do, and one of the most important things we like to do next is unsupervised learning. And this is from Jan LeCun's laboratory. They call it FAIR, Facebook AI Research. Jan and his team, Sumit Chintala, is doing work in unsupervised learning. And they're making really fantastic progress. This is using deep convolution, generative adversarial networks. That's a mouthful. That's a mouthful, okay? DC-GAN, otherwise known, DC-GAN. They made incredible progress, and the results are actually quite surprising. And basically what you do is you blast your network with a whole bunch of data. And this network eventually figures out what's important features. And so to show you an example of what we can do with that, Mike Houston, who heads up our AI work, Mike, why don't you stand up so they can just barely see you. Okay, there's Mike Houston. Mike is going to give us a demo of DC-GAN, of Sumit's work out of FAIR. And I think the demo is coming up, right? Let's take a look at it.
So what you see here is we're pushing 20,000 images from the Romanticism period through the network, and we're going to attempt to get it to learn how to generate these types of paintings on its own. So this isn't sort of the weird LSD trip type stuff that you've seen out of DeepMind. This is designed to actually effectively learn how to replicate these styles. So
okay, so first of all, we have tens of thousands of what, 12,000, 10,000 images like this of the same style?
That's right, 20,000 that are from the same art style, that's right.
And now we didn't label any of this stuff. We just simply took all this data and we shove it into this machine.
That's right. So it allows us to generate specific things. So for example, we can generate a landscape photo. So this is completely generated from the neural network based on what it's learned. So
now, Houston, let me just do this one thing. So we took these 20,000 images from the Romanticism era. We trained our network with it overnight. Now, after the network is trained, ladies and gentlemen, what's happening here is this. After this network is trained, what Mike is doing is he simply say, draw me a landscape. Now just wait, just think about this for a second, okay? Suppose you're a human, and I showed you all these images. And the next day, I say, draw me a landscape. And that's the landscape you draw. I mean, that's pretty amazing. This is a neural net, this is a computer. Apparently, it has artistic skills. It had figured out enough features of Romanticism landscapes that it can actually draw this landscape. Okay, go ahead.
So I'm partial to pastoral images, so we can also generate something that looks sort of like what you see on a farm with a nice big oak tree.
And so you guys type in farm. What did you type in just now?
So this is a combination, actually, of landscape and a forest.
Okay, landscape and forest, and boom, that thing shows up. Okay.
So and we can do beaches.
And so you type in draw me a beach, and that's what shows up.
But it's actually even more powerful because this is a generative network. We can actually combine things. So let's show you, let's say we want to take a sunset. We want to actually subtract out the fluffy clouds in it, and then add back in the beach. And then we actually end up getting a sunset at the beach. So this is the power of these generative models, is you can begin combining them together to say, give me something that looks a little bit more like that, less like that, take this, add this, subtract this. And it generates this on its own based on the generative models that it's learned.
Now remember, this network in the final analysis is still math. And so you could apply mathematics to this network and cause it to generate new images. I mean, this is really, really quite amazing. What a great piece of work. So Anyway, Sumit and the guys over at Facebook did a great piece of work here. This is one of the early works that is done in unsupervised learning, and you guys know that this is how a lot of us learn, and because there's so much unlabeled data in the world, if we can crack this nut, if we can crack this, this is going to really, really accelerate the progress of network learning. Okay, unsupervised learning. Good job, you guys. Supervised learning, unsupervised learning, recurrent networks, long short-term memory, imagination. There's so many more things to do. Reinforcement learning. There's so many things to do. Transfer learning. Today, we take an enormous amount of computational horsepower to train the network. But in the future, you wouldn't want to be trained a priori. You want to be training almost all the time. And in fact, you might be looking at images, learn about it, right there in real time, and adapt your action accordingly. So what uses a supercomputer, we want larger and larger networks, more and more complex networks, more and more richer networks, and we want to train it with more and more data. We want to be training it with almost real-time data. So these supercomputers that are now being used needs to be way, way bigger. On the other hand, we would like to do deep learning in real time. We would like that autonomous machine, that robot, to literally be studying all the time and reinforcing its network, learning in real time. For example, the Brett robot is thinking in real time. And so the amount of computation it does isn't just about recognizing the image. It has to figure out how to recognize the image and apply its motor skills repeatedly to figure out the proper action. We simply don't have enough computing horsepower.